I said any questions over yesterday's discussion, but yesterday's discussion was mainly E2, E1, S1, SN2. So this is Monday's lecture. Addition reactions, or maybe these aren't, maybe one's an addition, maybe one's not. Definitely reactions with alkenes. Nobody wants me to come look at their papers. All right, here is potassium permanganate, and under these conditions, it does the same thing that osmium tetraoxide did, but osmium tetraoxide is volatile, toxic, and expensive. Potassium permanganate's relatively cheap. So here is syn addition for a diol. Well, that one got me warmed up. So here's what we want to compare and contrast. I tried to do it in the PowerPoint slides. When this is cold and dilute, you get your syn addition of two OHs, you make a glycol or a diol. Here when it's hot, it oxidatively cleaves this bond. As an intermediate, you might have this aldehyde here that gets oxidized. And so this ozonolysis is a little superior because it stops at the aldehyde stage. So we can get the aldehyde. So we should have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. This methyl group is the methyl group there. So ring openers and ring closers are some of my favorite reactions. Ring opening, ring closing, lots of fun. Yeah, that was the last two things. Reduction of the ozonide. What else can alkenes do? Well, they undergo addition reactions. What if they undergo an addition reaction with themselves? When that occurs, we call it polymerization. And the alkane by itself we call a monomer. Then as we stick them together, we form a chain, and we call the chain a polymer. And there's all different types of polymerization. It can be started with a cation or a free radical or an anion. So here is isobutane. We can imagine these electrons grabbing a hydrogen off the sulfuric acid. Then we get a carbocation. So now we have an electrophile tacking a double bond. So these electrons grab that and we form a bond right there. And now we have what we call a dimer. Notice that's going to produce a carbocation right there on that carbon. And then that can encounter a third monomer and we can form this trimer. And this thing can keep going and going. And so a lot of polyester, polypropylene, polystyrene. Polystyrene has a trade name called styrofoam. And this can just go on for quite a while. And then finally, there can be a termination step. Chain growth ends when a proton is abstracted by the weak base of the acid used to initiate the reaction. The loss of hydrogen forms an alkene and ends the chain growth step. So this is a termination step. Here is a peroxide. A little bit of heat. Phenolphthalic peroxides for their free radical initiation to initiate a free radical reaction. So here is styrene, and we get a radical, and that can attack another styrene, and then that can attack another styrene, and pretty soon we have a big long chain. We call it polystyrene, and if we're Dow Chemical, we sell it as styrofoam. So what happened in lab this week? So this is what happened in lab last week. What's the name of this mechanism? Let me give you a hint. Starts with uppercase E. Yeah, you have a 50-50 chance. Since I see a carbocation intermediate, it's going to be E1, and I think you need this in your lab notebook as part of the write-up. All right, so we've made some cyclohexene. Here we have water leave. Whoops, don't want to do that. All right, this could go on for a while, but to relate it to what we just saw on the slide, this thing is polymerizing. So how many of you noticed towards the end of the reaction you had this gooey gum in your round bottom flask? The gooey gum was this side reaction, and so you get a bunch of these and you get this big gooey mess. And sometimes it turns green, and I think it's due to a magnesium complexing with this gooey mess that forms. In the old recipe, we'd have the students make their own 9 molar sulfuric acid, and they would typically take tap water, which has a lot of magnesium, and we got greener gooey messes. The 9 molar I made up for you, I used distilled water. So that explains the green gooey mess. Other interesting things to do with alkenes is this thing called Olefin Metathesis. Now, possibly in Chem 1, your double replacement, your teacher might have used metathesis in there because it's like an exchange. So here's an alkene, here's another alkene, and if we chop this one in half and chop this one in half, we can put together the two ends. So notice I've taken this end here and connected it with this end here. We can think of a double bond as two alkyl groups. Olefin metathesis is any reaction that trades and inter-exchanges alkyl groups. So I would just call this propene. Here's the common name. So if I think about slicing this in half and then taking another one and slicing it in half, if I put these two ends together, I get an ethylene. If I put two of these ends together, I can get a 2-butene, both cis and trans. So the catalyst used for these two things is a Schrock catalyst, named after the guy who discovered it, and another catalyst here called the Grubs. And I think there's been lots of patent battles for a long time over these catalysts. So here's styrene, and here's something else. If I chop that and chop that, put these two ends together, I get the ethene, and then it's putting this end and this end together right there. So earlier I mentioned ring openers and ring closers. So I chop this off and this off, get my ethylene, and then I can bond those together. So this would be a ring closing metathesis cross catalyst. And here is norborine. And if I think about chopping this in half, and then I can take another one and I can connect two up. And so this is actually a polymerization. Polymerization right here. What if we have a triple bond? What do we call that? We call it an alkyne. I had an old Subaru Loyal sedan that I bought in graduate school for $5,600. It's the first car I ever got payments on. I was newly married. And I had a bumper sticker and it said it takes alkynes to make a world. And then I sold it to somebody and they scraped that off because they didn't take chemistry. They didn't get it. It takes alkynes to make a world. So here's the general formula thing. However many carbons, go 2 times that and then subtract 2 to get your 2 elements of unsaturation for each triple bond. Some reactions resemble the reactions of alkenes, like addition and oxidation. Some reactions are specific to alkenes. Alkynes. So how do we name these things? Like always, find LCCC, the longest continuous carbon chain. And you want to find the one that has the triple bond in it. Chop off ANE and add YEN. Change ane to ine. Number the chain starting at the closest to the triple bond. Give branches or other substituents a number to locate their position. So, 4-carbon chain, got the triple bond right at the beginning. I would just call this 1-butene, or you can call it but-1-ine. And here's another 4-carbon chain. This is but-2-ine. And we call this a terminal alkyne, because this hydrogen is at the end, or the triple bond's at the end. We have this hydrogen sticking out. Now this hydrogen is very special because it's acidic. All other functional groups except ethers and halides have a higher priority than alkynes. So some common names: methylacetylene, isobutyl isopropyl acetylene. When you any welders, if I said oxyacetylene torch, would you know what I'm talking about? So we're going to look at acetylene in a second. So here's the common names: methylacetylene, it's a terminal alkyne; isobutyl isopropyl acetylene. Physical properties are going to be similar to all our hydrocarbon stuff: nonpolar, insoluble in water, soluble in most organic solvents. Boiling point increases as molecular weight increases due to more London dispersion forces. Less dense than water, will float on top of the separatory funnel if water's in there. Up to 4 carbons are gas at room temperature. And now we'll talk about ethine, commonly called acetylene, used in welding torches. The oxyacetylene flame reaches a temperature as high as 2800 degrees Celsius. It is thermodynamically unstable. When it decomposes into its elements, it releases a whopping 234 kilojoules of energy per mole. Where do we get acetylene or ethine? Well, it says here we can heat coke with lime in an electric furnace to form calcium carbide. And when I made this slide, I decided to add this chemical equation here so you wouldn't think I was talking about freebasing. So this is like almost like coal. If you go to the health food store and get activated carbon, like charcoal, that's what coke is, charcoal. And here is lime, which is basic, and you heat this up, you get carbon monoxide, and this here is called calcium carbide. And when this reacts with water, you get your acetylene. Of course, nowadays there's a little more sophisticated ways to make it. Synthesis of acetylene from natural gas, real hot temperatures, no oxygen, 2 methane molecules, undergoes this thing here, gives you hydrogen gas. What's the molecular structure look like? Since this is linear, you can tell me it's sp hybridized. Triple bonds are carbons that have sp hybridized orbitals. Sigma bond is formed between the carbons by the overlap of sp orbitals. Sigma bonds to the hydrogens are formed by using the second sp orbital. Overlaps of hydrogens s orbital. I always think of a Venn diagram and putting electrons in there, and that staples it together. I know that's wrong on a molecular level. And so a nice linear molecule. Then of course, each carbon then has 2 leftover atomic p orbitals. And it's that parallel arrangement which give you the pi bonds. There's one pi bond that's orange, and this other pi bond that's purple. And that is all for today. Thought I was going to end, and then I looked at last year's exam 3, and we're behind. I thought we were too.